Suppose we have a function f of t that represents some kind of periodic sound wave. Sound is actually a fluctuation over time in the pressure against your eardrum, and so really you can represent any sound as a function with respect to time, where the function just tells you the pressure against your eardrum at that particular time. So in general, any sound wave is going to be made up of a sum of many different frequencies. So you might wonder, well, if we have some incoming sound wave, how could we analyze it into all of its component frequencies? Just the language that I'm using to talk about this problem makes it sound kind of like we're treating this like a vector, and we're asking about the components relative to some basis. So that gives us a way to think about this problem. Maybe we could phrase this in terms of some vector space and have some convenient basis for that vector space, and then find components relative to that basis. We would have one component maybe for every frequency. Well, it turns out that all of this is possible, but we do need to make some additional assumptions about the situation that we're in. So here are the additional assumptions that we're going to make. So first is that our function is periodic with period 2 pi. That might seem like a pretty severe restriction at first, but we could, no matter what the period of this wave function is, we could rescale it so that its period is 2 pi. We could do our analysis and then scale everything back. So in practice, this actually isn't a real problem. We're doing this just so that we can concentrate on the interval from 0 to 2 pi. In general, a periodic sound wave with domain all real numbers is going to be hard to analyze because its domain is so large, but if we concentrate just on one closed interval, then things get a lot easier. In particular, we can do integrals without having to worry about whether they blow up to infinity. The other thing that we're going to assume about our function is that it's piecewise continuously differentiable. So you know what differentiable means. What does continuously differentiable mean? Differentiable means that this function has a derivative. Continuously differentiable means that this derivative is continuous. And then piecewise continuously differentiable just means that there actually might be a few isolated, on the interval from 0 to 2 pi, there might be a few isolated points where the function is not differentiable, or in fact not even continuous. But as long as there aren't too many of these points, then it's okay. So, right, this function, for example, it's not continuously differentiable because it's not even continuous, but it is piecewise continuously differentiable because, right, it's maybe I need to make it periodic, so let me go like that. There's this discontinuity here, but this is at an isolated point. And then there's also a discontinuity here. I've drawn it going straight down, but of course a graph can't go straight down, so it has to actually jump from up here to down there. So this is another discontinuity. And then there's a final discontinuity right here, where it jumps back up. But other than these three isolated spots, this function is continuously differentiable, right? All the way through this interval, it's continuous, it's differentiable, and its derivative is continuous. And then on this interval, its derivative is continuous, and likewise here. So again, in practice, this is not a very big, not a very restrictive assumption, because, right, physical sound waves are pretty much always continuous. In fact, they're pretty much always differentiable as many times as you wish to differentiate them. So in practice, neither of these are very big restrictions. So with these restrictions, we can actually write down the vector space that we want to talk about. So what we're going to work with is this vector space, I'm calling it V. It's the vector space of piecewise continuously differentiable functions on the interval from 0 to 2 pi. Now you might notice that I haven't said that they have to be periodic, and that's just because we're concentrating on one period, so we're sort of implicit in this is that outside of this interval, we're kind of assuming that it's going to just repeat itself. So it turns out that this collection of functions, so the constant function 1, together with sine of mx and cosine of nx, and m and n are just positive integers here. So z plus, this is the positive integers, so 1, 2, 3, 4, and so on. It turns out these functions sort of form a basis for this space, and I'll say what I mean by that in just a second. But notice that this is infinitely many functions because we have this function, the constant function 1, that's just a single function. But this function, sine of mx, this is shorthand for many different functions. There's sine of x, sine of 2x, sine of 3x, and so on. And then also cosine of x, cosine of 2x, cosine of 3x, and so on. So this collection is actually an infinite collection. So you might wonder, well, in what sense does it serve as a basis for this vector space? Is it a basis in the usual sense? And the answer is no, because not every piecewise continuously differentiable function is a linear combination of finitely many of these functions. So this is actually a slightly different flavor of basis where we're going to allow ourselves to take infinite sums of, or infinite linear combinations of these basis elements. For a normal vector space, that isn't allowed, but this vector space is, since it's infinite dimensional, it has a little extra structure that lets you make sense of infinite linear combinations. I don't want to get too deep in the details here, but the idea is that this is a basis. This acts like a basis if we allow ourselves infinite linear combinations. In addition to having this basis, this vector space also has an inner product. It's the familiar inner product on a space of integrable functions. So the inner product of f and g is just the integral from 0 to 2 pi of f times g. So I won't work these out in detail, but it turns out that using this inner product, the norm of these basis elements works out like this. The norm of the basis element 1 is just the square root of 2 pi. The norm of cosine nx, no matter what n is, all of these norms turn out to be the square root of pi, and then the same thing for sine. All right. Well, we have a basis. We have an inner product. You might imagine that what we should really want, since we have an inner product, is an orthogonal basis, or maybe even an orthonormal basis. So if these are going to be our basis elements, we could normalize them just by dividing by their own norm. But we also might want them to be all orthogonal to each other. So what about orthogonality for these basis elements? So to check if they're orthogonal, and if they aren't orthogonal, to do Gram-Schmidt orthogonalization on them, we need to know what the inner products of all of these are. And there are 3 flavors of inner product to do. There's an inner product where we have one of these sine functions and one of these cosine functions. There's one where they're both sine functions, and then there's one where they're both cosine functions. If they're both sine functions or both cosine functions, we actually get to add an assumption that these m and n aren't the same, because if m is equal to n and we have both sine functions, then this integral is really just the square of the norm, and we already know what that is. So for these two, we're going to add an assumption that m is not equal to n. And then for each of these, we have to work out this integral. So let's do at least one of these. So integral from 0 to 2 pi of sine of mx times cosine of nx dx. Now, in general, since we have an integrand with some trig functions, you might expect that we're going to have to do some trickery with trig identities, and indeed we will. There are these 3 product to sum identities that all come from the sum and difference formulas for sine and cosine. If you just rearrange them in various ways, you get these identities. And you can see that they'll let us turn a product of sines and cosines into a sum of sines and cosines. And of course, sums are easier to deal with in integrals than products are, so we'd prefer sums. For this one, since it's a sine times a cosine, we're going to need this identity right here, although you can see for the other 2, there are corresponding identities that will help. So for this identity, mx right here is playing the role of theta, and nx is playing the role of phi. So let's rewrite this integrand. We get integral from 0 to 2 pi of, let's see, 1/2 times sine of theta plus phi, so that's mx plus nx plus sine of theta minus phi, so mx minus nx. Yes. dx. Okay. Well, we can simplify this. So this, move that 1/2 outside, integral from 0 to 2 pi of, so this first sign, that's going to be sine of m plus n times x plus sine of m minus n times x dx. Okay, now there are two situations that we have to worry about. In one situation, m is equal to n, and in the other situation, m is not equal to n. So let's look at the situation where m is not equal to n. Okay, so if m is not equal to n, then we can go ahead and just do this integral. Remember, m and n are constants. X is the variable here. So when we integrate, we get minus 1 over m plus n cosine of m plus n times x. And this is from 0 to 2 pi. Okay. Oops, I'm missing a term here. I need the rest of it. In fact, I'm going to need some more space, so let me use this whole line. Plus sine of, sorry, no. So now I'm integrating this. So this term, it gives us that integral. This term gives us 1 over m minus n. Sorry, I need a minus cosine m minus n x. There we go. I got it. 0 to 2 pi. Okay, and we do have to be careful when we have things showing up in denominators. So is it okay to be dividing by m plus n? Well, remember, m and n are both positive integers. So m plus n is definitely not 0. For m minus n, well, we are assuming we're in the case where m is not equal to n, in which case m minus n is definitely not 0 because m isn't equal to n. So both of these things are okay. So now we can just finish evaluating. But you see, when we plug in 2 pi and we plug in 0, cosine will give us this cosine of m plus n times x. Because m plus n is an integer, when we plug in 2 pi and when we plug in 0, we get the same thing. So this is going to give us a 0 right here. But then the exact same thing happens right here. M minus n isn't 0. So this is a non-zero integer in front of our x here. So when we plug in 2 pi and when we plug in 0, cosine is going to give us the same thing. And so this part also comes out to 0. And so we get 0. So this whole mess, sorry. So we're almost done. We're done with the case when m is not equal to n. Now we have to check the case when m is equal to n. Right? So now we have to back up to this step and do it again, but assume that m is equal to n. Well, if m is equal to n, let's rewrite this integral one more time before we actually do the integral. If m is equal to n, we get sine of, that's a sine of m plus n is 2mx plus sine of m minus n. Well, if m and n are equal, m minus n is 0, so this is sine of 0, which is 0, right? So this part just goes away. And now we can integrate. We get 1/2, 1 over 2m, I guess a minus sign, cosine 2mx. And then again, when we plug in 0 and 2 pi, we get the same thing from this cosine part, and so this whole thing comes out to be 0. All right, so now we know that all of these sine functions and all of these cosine functions are orthogonal to each other because this inner product is 0. So I won't work out the sines and the cosines, but it's a nice exercise to do. If you're looking for something to do on a rainy day, you can use these identities to evaluate these inner products, but I'll spoil the surprise. You do turn out to get 0 for all of these. So this basis for this vector space that we have, right, this basis for our vector space, and again, quotes around basis, because we have to take infinite linear combinations for this to be true, but we have to take infinite linear combinations to be able to produce any vector in this vector space, although there's a slight caveat to that too, but that's the general idea. This basis is an orthogonal basis. All of these basis elements are orthogonal to each other, and we could make it an orthonormal basis just by dividing by all of their norms. So now that we have an orthogonal basis for this vector space, that's going to make computing the components of any given vector in this space with respect to this basis much easier, because we can use the inner product to compute the coefficients for the components.